You have a system. So in your case, the system is a robot, but the word system is general terminology, right? It could be a chemical process, anything, mechanical system, electrical system, and we're trying to control it. So the first thing is you have to identify what variable you're trying to control, right?
Yeah.
So typically in controls, if I remember it, it's been a while since I taught the class, I believe it's called C. C is the symbol allocated to that. So you're trying to get C to behave like you want it to, right? So there are two aspects to it, right? C, there is an actual C, right? That's what is exactly happening at the output of the system. So maybe it's velocity, right? So there is a velocity that is currently prevalent, but you want to change it to C desired. So you're trying to close this gap. That's what control is about, right? You pick a variable that you want to control and you make the actual value go towards the desired value. Now how do you tell it what the desired value is? You do so right here. So this is R. I think it's called R typically. I could have swapped these two, it doesn't matter. So you go to sample C and create an error signal. So E of t is equal to R of t minus E of t. You get the idea of an error? This R of t is what we want. And this is what we have. What we have, what we want. We want the what we have to try and line up with what we want, right? So without creating this error signal, you have no chance of controlling that signal. How is that? So let us take an air conditioner. So suppose I say I need to reach a target temperature of let's say 24 degrees centigrade, right? So I just turn on the AC and keep it on for 15 minutes and turn it off. Now that's not a closed loop control system, because what is missing is you have to monitor the temperature in the room. Just turning it on for a certain amount of time, there's no guarantee that the temperature in the room is going to reach what you want it to, because it depends on the outside temperature. Like the walls are what? The heat is coming in at different rates depending upon the outside temperature, right? So unless you pay attention to the quantity to be controlled, how can you control it? You can't. But you used to have ACs in the old days like that. You would keep it on for a while and then you would turn it off, right? Sometimes it would become too cold because that amount of time is too much for the conditions. Maybe it's not that bad outside. So if you keep it on for 30 minutes, maybe it's too much and it lowers the temperature below 24. So unless you set up a loop, you can't control the quantity. Alright, now there's something else missing here, because you need to have a controller here. So this is the controller. So E of t, the error signal, is used to generate an input to the system that modifies that so that the error becomes small. It's not always possible to make the error zero. I told you in the real world, you cannot have perfect anything, a perfect control system, whatever. So typically what happens is the error will oscillate, meaning that sometimes C will be below R of t, sometimes higher than R of t, but hopefully it tracks. If you have a closed loop control AC system, at night when you reach the target temperature, it will turn off for a while, right? And then it will come on again. So there's a little bit of oscillation of the error signal. You know what I'm saying?
Yes.
So, but you don't want to have it turn on and off all the time because you'll go crazy. You won't be able to sleep. So they have methods to create a dead band so that it doesn't turn on immediately. It allows the temperature to go a little bit below and a little bit higher. The two thresholds are triggered at different times. I can only explain if there is a thing called chatter. You don't want control system to chatter. And so there's a way of preventing that, because you don't want it to constantly turn on and off, right? You want, maybe it's off for a few minutes and the temperature rises and then it comes on, because otherwise you will not sleep. Okay, now, so this is the closed loop control system. Now, how is that going to change whatever it is you are implementing? So you are implementing the control loop based on what? Time that you drive it, right? But how do you know time and distance are proportional? You're saying I have a constant velocity. Do you really have a constant velocity? Because the robot is initially stationary and then it speeds up to 0.4 meters per second. How could you have a constant velocity? At least for that first part, the velocity is not constant, right? But then you're saying, okay, I will ignore that, but after that I have a constant velocity. Not really. When you drive a car on the road, next time try to maintain a constant velocity. Even the cruise control system cannot maintain a constant velocity, because the road surface is uneven, right?
Yeah.
Sometimes it's rougher, so velocities will drop, and then the control system will act and push it up again. But that means the velocity can't be, the average velocity cannot be constant. So the only way you can ensure distance is by monitoring distance, not by monitoring time, because that assumes that the velocity is constant. So you have to monitor distance. The loop has to be driven by distance of travel. Now how would you do that? So you have to do what? You have odometry, right? So won't that allow you to measure the total distance traveled? So that's how you should really do it. Now the program you are implementing for the C, you are still doing open loop. You are saying I'll figure out the different times and then I'll, but really what you should be doing, and maybe for this particular example it'll be easier, is to graph it, and then maybe you can figure out the lengths approximately, and then you create a loop based on distance and not time. So if you sketch it out on paper, you still have to figure out the radius. There's no easy way to do it except by trying it and then changing it if the C doesn't look right. You know what I'm saying, right?
Yeah.
If the C is too flat, how do you make it sharper? You make the radius smaller. So for that, you have to decrease V. Is that clear? So that's why I said you have to get some figure there first. You have to get something there. And if you've got the right segments but they don't look right, then you can change the curvature accordingly. But truly, it will be better to do it with distance. But time also will work. Time should work. But it's not as good as a closed loop system. So do you understand what a closed loop system is? So the first thing tomorrow, what we'll do is, we'll get into a different M file, a MATLAB program, and we'll do a closed loop system where we go around an equilateral triangle. So an equilateral triangle is one where each angle is 60 degrees. Maybe 3 meters. So the robot is going to start here. That's a diode. I don't know why I drew a diode, but robot. And then it's going to go here. So what would be the crudest way of doing this? I would do the same thing as the circle program is doing. I would say go forward for 3 meters, right? But I'm not going to measure the 3 meters. I'm going to say I know my velocity, so I know the time taken to cover this, drive for that distance. So that's like counting what? Steps, but not looking at the distance you've covered. Counting steps is not repetitive, right? Do you realize that? When you're tired, you take shorter steps. But right there, if you're running the steps, you take longer steps, right? So steps doesn't mean anything. That's why, you have the speedometer applications. And the first thing they ask you to do is to calibrate your steps. It never comes out right, even after calibration. Sometimes you think you haven't moved very far, and then it says, you got 1.5 miles. I mean, I'm talking about the poor quality apps, right? But it's very difficult to calibrate steps, actually. In a repeated way, you want to get the same answer. It's very difficult to do that with steps. So, you really want to do it differently, right? And how do you want to do it? You want to do it, by the way, one other thing. The gazebo robot adds noise to the wheels. So that often when you're asking it to drive straight, you find that it's slightly inclined. It won't remain on the straight line. It might end up here. Next time you run it might end up here. And that's a problem, because immediately you won't be able to recreate the triangle. Because, let me back up and say, how would I drive it in a very crude manner? I would go forward 3 meters, not forward towards this node, just forward 3 meters, because I trust my forward. So you'll end up in different places, right? At that point, I'm going to turn through 120 degrees. It's not 60 degrees. You have to turn through this angle. So then I'm hoping I'm pointing to here, but already you're off. And then I'll go forward 3 meters. You're probably going to end up somewhere here. And then I'm going to turn 120 degrees, right? Do you realize the problem? You will never be able to close this triangle. When you try it multiple times, it will remain unclosed in different ways. So that's not a way to drive, because you're driving open loop. So strictly speaking, you should be heading to this node. So you have to monitor two things. You have to ask, okay, this node I'm producing here, right? You draw a circle around it. Maybe this is, sorry, not 0.02, that might be too tough, 0.2 meters. I'm saying if I'm within 0.2 meters, I have reached that node, right? So if I make it 0.1, it's tougher. I can't make it 0, right? You know that already.
Yeah.
Nothing in the world is perfect. So 0 means that you're going to have a hard time reaching that point. So that means if it crosses anywhere inside the circle, you're saying, okay, I've got there.
Yeah.
And when that happens, what you want to do is, so let me back up, I missed a point here. So you might not get into the circle, because if the robot veers like this, you're never going to reach that circle.
Yeah.
So do you realize when you drive, you have to not only monitor how far you've gone, but you got to point and drive at a certain target point. That's how we drive, right?
Yeah.
So therefore, I have to maintain heading control. As I drive, I have to ask myself, am I within the circle? At the same time, I have to say, am I pointed towards that circle? So it has to be two loops. The outer loop will say, have I made it inside the circle? But without the heading correction, you might never even be pointed towards the circle. So you have to have an outer while loop and an inner while loop. And then you don't want to stop and turn. When you stop and turn, you might get precision, but that's, if you're in a battlefield and people are lobbing artillery shells at you, you don't want to be stopping and turning. You want to go on the move, right? So what you want to do is, you want to keep driving, and when you achieve that, immediately you want to switch and say, I now want to go to that point. So imagine there is a circle around that also, and there is a circle around that. So it should be possible to write a closed loop control algorithm where I go around the circle. Now the circle is going to be slightly like this, because remember, you're going to turn on the fly, so it's going to look a little bit rounded at the corners, but that's okay. Because your idea is not to do a precise triangle anyway. You want to go quickly, so it's going to, the corners are going to look, how do we drive, right? The corners are always curved. I mean, you can't, your garage is here, you can't go here and then turn the car this way. It's not possible, you always curve. So that's what we're going to do. Tomorrow's going to be an interesting day. I don't know what the next topic is, but one thing that you got to keep your mind on is our first lecture. Remember, I broke down the robotics area into localization and mapping, kinematics and dynamics, right? Cognition. So we're going through those sub areas of robotics. This is not like a random recitation of topics. So today what we did was we understood what the kinematic model of a robot is and what changes are necessary to make it a dynamics model. And there's a lot of ground we covered today actually. Also the software environment should be a little bit clearer to you now. So the original structure, the structure of the odometry data is contained in odom. Pose. Pose. Position. So this is where the data is, right? So this is the data within the message structure. I'm just unloading it. I don't have to. I can use this original variable. I'm just peeling it off so that I can save it in a MATLAB variable that I'm more comfortable with. So what I do is, so deal, it takes these two and helps put it in an array. So help deal, you'll figure out what it is. It peels off the X position and Y position and it puts it in a MATLAB variable. I'm just comfortable with that. So this is the X position and this is the Y position. This odom is made up of 3 numbers, right? I said don't worry about the angle. So X and Y are peeled off, separated and put in odom pose 1 and odom pose 2.
Yeah.
So that's what it is. And then here, see, I think I'm overdoing it because I could have accumulated it in odom pose 1 and odom pose 2, but then I decided I'll put it in X and Y and keep on incrementing X and Y. It's a little bit, it's not the most efficient of programs, I always like clarity, even if I'm wasting a few extra variables, more memory, I don't really care because I want it to be clear. So after putting it apart, I did this. Maybe it's not needed, I could have directly gone to X, Y. Now, so this is like, your first prayer in a day or something. Anytime you open a MATLAB program, you have to clean up your workspace. Otherwise, so even if I go here, you see, all these variables are still here. Wherever I go, any program.
Yeah.
So if you run this program without the cleanup, then if there's any conflict, it's going to go use those variables. C++, it doesn't happen. When the program ends, it's over. That's it. That's why C++ has disadvantages compared to MATLAB and Python. So clean up. Then ROS shutdown I already explained to you, right? So this is where you connect with ROS from MATLAB. You have to get the IP address. I have a static IP address, so I don't need to change this. You might have to change it.
Yeah, we change it.
So the IF config will tell you what your IP address is at that time. So all this is standard. You just have to copy it. The only thing you modify is the IP address, if at all. Then after that, you come to the publishing subscription block, right? Because you can't run a program in MATLAB that talks to Gazebo and ROS if you don't have some topics that you're interested in. So there's 2 kinds. There is the command well. So that's how you're going to give commands to the robot. And then there is the odom, where you get position information from Gazebo. So the model state, I told you what it is. It's a way of knowing the true position of the robot. I just put it in there. Sometimes I'm not using it, sometimes I'm using it. I just leave it in there. You can remove it if you want. Is everybody clear?
Yeah.
So these are all automatic. Then I create an instance of the pubwell message. So this just gives you the object, and then you have to create an instance of that. So I don't know much about object-oriented programming. I just do that, and I talk the talk because I picked up this, buzzwords. So you create an instance and then you populate it with the variables. So see, I do it in my own clean, neat way. You don't need to do that. I can directly push the velocities into the well message structure, but I first create this, and that helps me calculate the radius. So everything is clear. The circumference is 2 pi r. You don't have to do circumference because you're doing pieces of circles. Then I calculate the time. Now you're going to do this multiple times within the for loop, right? Because you have many circles. So each time you're going to come up with what percentage of the circumference. So maybe it's 20%. So you put 0.2 c by velocity. Got it? And the velocity is going to be different because you want different radii. So you will be changing the velocity. I just set it here and forget about it. So this will be happening inside the for loop but outside the while loop. Got it? For loop, while loop. So it's happening between the two. Okay, so here's where I'm packing the variable, the data structure with velocity and rotation rate. So there I just defined it for my own sake. Here I push it in. Or down. When I say receive, I get the latest data. If I don't say that, it'll be just the first point. So every time I have to say receive, because that means give me the latest. Same thing with model state. And then over here, I do the same thing again, right? No, not the same thing. I explained this to you earlier, so what I meant to say. So ODAM pose 1 and ODAM pose 2 is deal. Got it? Then I initialize the plot variables, x and y. Now, let me go over this ROS rate again. So it is an attempt. If you don't like it, remove it. You can run the loop as fast as you want. Nothing's going to change. But it's just good practice. In real-time systems, you don't want to be running every loop as fast as the computer can run it. You really want to run a LiDAR loop at a different rate from an image processing loop, from some other loop. That way you manage your time much better than if you run everything as fast as the computer can run it. So this is the way you do it. You define a ROS rate object which is going to run at 10 Hertz. And then you initialize your time and then you say, okay, reset the stopwatch. So now it starts counting. And then while RTT, so RTT is 0, TC is some finite value, so it's going to say true and it's going to start doing this, right? I need to update the RTT, which I do by extracting this part of the structure. There is, now I'm not making this up, it's all in the L file for the ROS rate. So this gives me the elapsed time. Is it okay? And then I say robot drive. So send. Only if you send the velocities will it drive. Otherwise it's not going to care what velocity variables you set up. So when you send it, it starts moving. Now I'm refreshing the ODAM. Does that make sense?
Yeah.
So the same receive sub ODAM gives me the latest frame. I unpack it, I push it into X, but this time I'm augmenting it. See? The old X, I add on the new value. So it gets longer and longer and longer so that the entire circumference of points is available to me for plotting. And then wait for R just burns off the rest of the time so that you only execute it at a rate of 10 Hertz. That means once every 100 milliseconds, this loop is executed. You know what the time they use for self-driving cars? It's 10 times, 100 Hertz, because you're moving much faster. So you cannot afford to be slow. So the loop time is 10 milliseconds. Now, why not 2 milliseconds? Now remember, you have finite resources. So you don't just go crazy because you don't know what the right number is. There is the right number which you can find for every application. And you run it only as fast as that. So people seem to have settled on this 10 milliseconds for self-driving cars. So it's like 10 times. This robot is not going very fast. So I bet you even 10 Hertz is too much for it. You can probably do 5 Hertz because it's so slow. So you can run the loop much slower actually. Nothing great is happening in the life of this robot. So burn the rest of the loop time and then it will only come out when RTT has done the whole circumference, right? And then this is one instance where the robot loop is complete. You don't have to control C. It's a finite loop. Mission accomplished when it goes all the way around. I stop the robot by setting the velocities to 0. If you don't publish it, no change. You have to publish it. And then you saw how the robot kind of goes to the side sometimes when you stop it. I was going to show you something. Maybe I'll show you this and then we'll go to that, okay? So I was going to run the program and you're going to watch this. We may have run it, but maybe I didn't make the comment I wanted to make. Oh, see that jerky thing? That's because of the slow refresh. It's not anything else. And it's not even working properly. The circle is not right. We didn't change anything, so I don't know what's going on. So maybe we kill it and run it again. It did. Yeah, now it's better. 2 meters, sort of. So that jerkiness is not, the screen is, it's an older model projector. Strange thing is earlier today
It was on for a long time, but it's really
see, this is the first pass. And then I stopped it and ran it again. So, let's do it again because I wanted to show you what ROS looks like. So, I've got to run this MATLAB and go to the ROS, forget the gazebo. So, you see this shifting lines here? It's getting a view of the cylindrical obstacle from now we can't see it again, it's out of range. You see that? It'll reappear. Now the orientation is different. You can change this to match up with the orientation of the gazebo. It'll come back. Well, it's here somewhere. No, I don't want. See, the keys are different also in ROS. I don't know why they did that, but gazebo and ROS, the pad seems to work differently. What happened to the LiDAR? There it is. If you wanted to create a map, right, you have to take those, you're looking at different sides of the cylinder, so you have to put it on the map. We're not doing it here, right? We're just looking at it and forgetting about it. But that's what mapping is basically. You have to pick up anything you see and put it on a map. And then you have to do it with the correct alignment. Isn't that true? Because the alignment is very important. The robot's angle with which the LiDAR is looking at the cylinder is changing. So you have to be conscious of all that. Not you, but the program has to handle it through transformations. Otherwise the map will be all over the place. So this is something that you have to be very aware of in mapping. Because when there is an obstacle, right, which is a moving obstacle, if you put it on the map and leave it there permanently, it's a problem. Because soon the whole landscape will be filled up with obstacles which were there but which are now gone. That's why mapping involves sampling. So every square, you're sampling the space around that, above. So after a while, if you don't see it, you remove the obstacle. Otherwise, you'll create a map filled with obstacles, ghost obstacles. Because moving obstacles are not permanent obstacles. So you'll create a map with ghost obstacles. So mapping is a sampling operation. That's why you have to have a high-speed sampling unit. LiDAR is quite fast. So you keep eliminating if you don't see it there. If you see it there, you keep augmenting. So that's how a map is created. The map is not 100% certain. Maybe it's 95%, but that's good enough. Because that's how we drive. We see people dashing out from the side of the road, right? And we have a mental map of all that. So we're trying to get a computer to do the same thing. If I can give you a piece of advice, right? So knowledge is only accumulated incrementally. If knowledge was so easy to accumulate, you can finish that sentence. Then everybody would be knowledgeable. So because knowledge has to be accumulated incrementally, only a select few are able to do it. So you have to have a building block. If you know ROS and you got it, your own setup on your computer with Linux and ROS, you can continue learning on your own. I told you the aim is to make you a self-learner, not to fill you with facts, because we don't have enough time in this world to accumulate all the facts, and it would mean nothing. If facts were not related in some way, it would mean nothing.